devices. And now we are going to see how the dual gate MOSFET is fabricated. So in dual gate MOSFET, as the name indicates, you have two gate terminals compared to in a conventional MOSFET, you have only one terminal, one gate, whereas in dual gate MOSFET, we have two gate terminals. So why I am going to use two gate terminal is to reduce my overall capacitance, gate capacitance at high frequency. We know that the CG is going to be playing a troublesome role at high frequency. I want to reduce the CG. So one possibility is I'm going to have two gates which are going to help me reduce the overall gate channel capacitance. So the voltage at both the gate terminals control the flow of current. MOSFET is a voltage control device. So VGS and VDS are going to control the current, drain current, which is going to flow through your MOSFET. And since now the device is going to have four terminals, you can be considering this device as a tetrode. Tetrode is a four-terminal device. It is a general name for a four-terminal device. Construction of MOSFET, you see, you are having an N-channel. It's an N-channel dual gate MOSFET. So you are going to take a P-type substrate. In the P-type substrate, you are going to fabricate three N plus regions. One is source 1. Okay, another one is drain 1 and source 2, which are going to be common region, and next one is drain 2. All are N plus region. So between source 1 and drain 1, you have a channel. Between source 2 and drain 2, you have a channel, and above the channel, you have the gate. When you take metallic wires from the device, from the gate you have two metallic wires coming out, G1 and D2, and from the source you have one S coming out, and from the drain you have one D coming out. The intermediate, so drain 2 and drain 1 and source 2, will not contribute to any terminal. They are just acting as a buffer. So this will complete the path from source 1 to drain 1. One channel I have. Between the gate, below the gate, I have one channel. From source 2 to drain 2, I have one more channel. That above that, I have my gate layer. And in between the metallic layers, I'll have my SiO2 silicon dioxide insulating dielectric layer between the terminals and the fabricated regions N plus in your thing. And for an N channel and do a MOSFET, this is the diagram. But since you have two gate, you have G1 and G2. And if the arrow mark is pointing inwards, it is N channel. If the arrow mark is pointing outwards, it is going to be P channel. The diagram by source and drain are going to be same. Even this symbol is going to be same. But only thing, instead of having one G here, I'll be having G1 and G2. Same as here. For P-type also, I'll be having G1 and G2. Understand that the main purpose of having two gate terminals is to enable the device operate at a very high frequency, which was restricted because of gate to channel capacitance. So see here the N plus region in the middle acts as a drain for MOSFET 1 and source for MOSFET 2. So two gates are in series. So when the dual gate MOSFET is used as a two series MOSFET, the effect is similar to connecting two capacitors in series. So you can see here you have one capacitor, here you have one capacitor. You have two terminals, one is gate, one is channel. In between you have dielectric. So you have one capacitance here. Okay, and you have one capacitance near gate 1 in this junction, and one capacitance in this junction G2. And these two are in series. These two are in series. As the total value in the series, when capacitor is in series, the equivalent capacitance is given by C equivalent equal to C1 C2 by C1 plus C2. The capacitance and resistance, they are opposite when it comes to formula. The resistance in series means you will add, but capacitance in series means you will use the formula C1 C2 by C1 plus C2. So when you have two capacitance, gate capacitance 1 and gate capacitance 2 in series, the overall gate capacitance become lesser than the least. So it will become very, very small. So by this process, I'm going to enable the device operate at a very high frequency. So in a dual gate MOSFET, I'm going to apply the voltage at both the gate terminals to control the drain current. So when the voltage is applied to the gate terminals G1 and G2 are greater than the threshold voltage, the channel is formed and the corresponding current is flowing. Other principles are same, but instead of having a single source VGS, I'll be having VG1 and VG2, which are going to control the drain current, which is going to flow through my device. Since I have two gate terminals, two voltages I'm going to apply at gate 1 and gate 2, which are going to control the amount of current flowing through the device. And if the voltages supplied are more than the threshold voltage, then only you have channel formation and you have drain current flowing. So for any device to work, the applied voltage should be more than threshold voltage, right? Then only the device starts connecting. The same is the case with your dual gate MOSFETs also. So see here, I have the transfer characteristics. So when I'm going to vary VG1 and I'm going to keep VG2 constant and I'm going to see the drain current, you see VG1, I'm going to draw VG1 versus ID and for different values of VG2. So as you increase the VG gate voltage, your drain current is going to increase. As you decrease it, you can see the drop in drain current. So when the gate voltage of either of the terminals is negative, the drain current decreases. You know the reason, because when you give a negative voltage, you will have equal and opposite charge. You will have positive charge here. Okay, but your channel is an n-type channel. So when you are going to reduce the number of electrons by introducing more and more positive charge, the drain current is going to reduce. So that logic is being justified here. So when I'm going to make any one of my gate terminals negative, my drain current is going to be very, very small. So the drain current gets enhanced when the gate voltage applied to both the gate terminals are positive. So only when the gate voltage applied to both the terminals become more than zero, you can see a significant increase in the drain current. Otherwise, till that point, the drain current is not increasing that much. So this is the reason for the variation of drain current with respect to gate. And this is going to be the transfer characteristic. Transfer characteristics means output current. I'm going to see what all voltages are going to control my drain current in my